infinite limits and vertical asymptotes. Our objective in this lesson is to be able to determine infinite limits from the left and from the right, find vertical asymptotes of a function, and make connections between the infinite limits and vertical asymptotes. An infinite limit is when the limit as x approaches some number of a function equals plus or minus infinity. What that really means is the function increases or decreases without bound as x approaches some number. Now it's important to make the connection between the fact that the limit as x approaches c of the function is infinity and the fact that there will be a vertical asymptote x equals c. So analytically, what that means is looking at a function, for this one as example, f of x equals 1 over x plus 2, you're going to know that you have a vertical asymptote when you get 0 in the denominator only, meaning there is no common factor with the numerator, such as in this one, what makes the denominator equal to 0? If we solve that, x equals negative 2. And x plus 2 is not also a factor in the numerator. Therefore, I know that there will be a vertical asymptote, and the equation of it is x equals negative 2. Obviously, when we graph that, we put a dashed line to show that because we're getting 0 in the denominator for negative 2, x can never equal negative 2, so there will never be a function value there. So graphically, an infinite limit is when we see a vertical asymptote. Now, because there is a vertical asymptote, we know that the way functions behave is that either the function will be increasing without bound as the x values get closer to that x value, or the function will be decreasing without bound, increasing or decreasing without bound. How can we tell? Well, one way is numerically. We can make a table of values, or a little bit quicker, we can observe the sign of the function at x values very, very close to the vertical asymptote. For example, near negative 2, but just to the left, we know that the function will either have to be way up here or way down here. So what is a value near negative 2 but just to the left? How about negative 2.1? If we plug that into our function, we will see the values and know that either they're very large or very small. F of negative 2.1 makes 1 over negative 2.1 plus 2. Now, I could compute the value, but really all I need to know is it a positive value or is it a negative value? Because if we're that close to the vertical asymptote, the function's either going to be way up here or way down here, either positive or negative. So I notice the numerator obviously is positive because it's positive 1, and the denominator, because this is a larger negative number than a positive number, adding them together results in a negative number. And a positive number divided by a negative number makes a negative number. So I know that the function will be decreasing without bound as we approach that vertical asymptote from the left. So I know the function is going to have to be headed down towards negative numbers. How about from the right? Let's pick a value very close to negative 2, but just to the right, like negative 1.9. So f of negative 1.9, 1 over negative 1.9 plus 2, that makes a positive value over a positive value, and a positive over a positive makes a positive value. So from the right, the function will be increasing without bound, going towards positive numbers. Now that we know the behavior of the function, we can write what the infinite limit looks like. The limit, as x approaches negative 2 from the left, this side of our function, equals negative infinity. And for this one, the limit as x approaches negative 2 from the right for f of x equals positive infinity. Now technically, these are limits that do not exist. But because we know the specific direction they're going, it's okay for us to say the limit equals negative infinity and the limit equals positive infinity. Let's take a look at some other examples. Find the limit as x approaches 5 from the left of f of x, the limit as x approaches 5 from the right of f of x, and the limit as x approaches 5 of f of x, analytically and numerically. Find the vertical asymptotes, if any, of the graph of the function. Here is our function, f of x equals x plus 5 over x squared minus 25. So remember, we want to take a look at the behavior of the denominator. Now, I know that x squared minus 25 can be factored. So I'm going to start by factoring the denominator, x plus 5, x minus 5. Now I notice there is a common factor. X plus 5 can factor out. However, anything that makes the denominator equal to 0 is going to give us some kind of discontinuity. So I'm going to take both of those factors, x plus 5 equals 0 and x minus 5 equals 0, and find those discontinuities. This gives us negative 5. This gives us positive 5. Now, because I could remove this one by factoring it out, it was removed. This gives me a removable discontinuity. And do you remember what that looks like in a graph? That's right, it's a hole. This one I could not remove. Therefore, this is going to give me a vertical asymptote. This is a non-removable discontinuity. I'm going to abbreviate, and therefore I know I have a vertical asymptote. So I've already done the second part, find the vertical asymptote of the graph of the function. Often it's easier to start with that. So my vertical asymptote is x equals 5. Now let's go back and find the limits requested. The limit as x approaches 5 from the left of my function. Now, I know that there is a vertical asymptote at x equals 5. Therefore, I know that this limit has to either equal positive or negative infinity. From the left, I can pick a value very close to 5 and observe the sign, positive or negative. What's a value very close to 5 but on the left? How about 4.9? So I'm going to take my function, and preferably the factored version, 1 over x minus 5, and plug in a value very close to 5 but on the left. So 1 over 4.9 is just to the left of 5 minus 5. That gives me a positive over a negative, and that makes a negative. So I know that it's negative infinity for the limit. Let's look at the other limit. The limit as x approaches 5 from the right of f of x equals, now again, because at 5 there is a vertical asymptote, I know it's either going to be positive or negative infinity. Let's pick a value very close to 5, but on the right. How about 5.1? Keep in mind what we're doing is like observing a table of values, but a little bit quicker. Obviously, the numerator is positive. This time the denominator is also positive, and that makes a positive. Positive divided by positive, positive. Opposite signs divided, negative. Therefore, I know the infinite limit is positive infinity. Finally, we've done that one. Now we do the limit as x approaches 5 of f of x. Because the left side was negative infinity and the right side is positive infinity, these two infinite limits don't match. Therefore, this limit doesn't exist. Let's get rid of this equal sign and write it properly. The limit of f of x does not exist. Number 2, find the limit as x approaches pi over 2 from the left of tangent of x. Now this one might be tricky unless you're very familiar with the tangent function. Often when I have a function that I can write as other functions, especially when I can rewrite it as sine and cosine, it's a good idea to do that. So I'm going to rewrite this problem, the limit as x approaches pi over 2 from the left of sine of x over cosine of x. Notice that gave me a denominator. And remember, when I get a denominator that equals 0, I get discontinuities. Well, where does cosine of x equal 0? When x equals pi over 2. Obviously, I can't cancel out cosine x with sine x. There's no common factor there. So that means that this guy is the equation of a vertical asymptote. Which also tells me that this limit is going to equal either positive or negative infinity. How do we tell which is which? Well, we could pick a value very close to pi over 2, but just to the left. Can you think of a value very close to pi over 2, but just to the left? How about pi over 3? So, plugging pi over 3 into the numerator, sine of pi over 3, and into the denominator, cosine of pi over 3. Remember, I'm not looking for values, I'm just looking for signs. Sine of pi over 3 is positive, cosine of pi over 3 is positive, and a positive divided by a positive is a positive. Therefore, I know that my limit is positive infinity. Thanks for watching.